Welcome to part one of chapter 4, where we're going to be covering the Solow Growth model. We're actually going to be covering the Solow Growth model through all of chapter 4, but it's a three-part lecture on this particular model. The reason I'm spending so long on it is this really is like the first building block for a lot of the other growth models and really a lot of the other models that we'll be learning about in this course. So I really want to make sure that you guys have a good, strong foundation to build pretty much everything else related to the course on from this. So we're going to be spending 3 lectures on this. And, I guess we may as well just go ahead and get started. So the Solow growth model was developed in 1958 by Robert Solow. Actually, probably developed a little bit before that. It was published, I believe, in 1958. Robert Solow is an incredibly influential economist. He got the Nobel Prize in economics. Really awesome economist. So anyways, enough about that. Last time we learned that growth occurs. We talked a little bit about why it occurs, but we didn't get so far into the how part, what's that big driving mechanism behind growth, and that's really the most important part because we need to know not just that growth is occurring, because you can just you can open a history book and see. You can turn on the TV and watch stuff from the 1960s, 1970s, 1980s and go, oh yeah, wow, things have really improved since then. So we know that growth is occurring. And, you've honestly seen it to some extent within your own lifetime. It's a fairly slow moving process, but it's not so slow moving that you're not going to see it in your own life. But how do you think growth occurs? Do you think maybe it comes from investing in capital? Maybe, letting a firm borrow some of your income to build up their company. And when their company builds up, they pay you that money back. And then that company, they get more business. Because they get more business, they earn more money. They earn more money. Their workers, get higher wages, and then they can go and buy more stuff, and there's increased demand, and the economy grows that way. Yeah, maybe, but maybe not. It's not really giving us the whole picture, because we're not looking at how ideas are driving growth. There, we're just looking at just making stuff for the sake of making stuff. And having more stuff is great, but the big question is how do we get that quote unquote more stuff? Naturally, we just make more of it. But the thing is, you can only make so much of that stuff before you begin to hit the productive capacity of your economy and you run out of available resources, whether it's physical capital or labor. So there's more to it than just having and making more stuff. There's also the power of ideas, man. And I'm not getting into that weird hippie shit where it's hey man, it's the power of thought. And if you think about something enough, then you're going to make it happen because of sympathetic vibration in space and in time, man. I'm not getting into that. I'm getting into the ideas of people coming up with useful ideas that other people can use. Think Doc Brown when he made the time machine, Rick Sanchez when he made that portal gun. I hope I'm not so old that Rick Sanchez is now out of relevance. Hopefully he's still relevant for at least a couple more years before I have to start trying to find new examples. But I'm sure we all know who Doc Brown is. If you want to go into the real world for a minute, think about guys like Steve Jobs, Bill Gates, Elon Musk. All right, these guys are driving, or if not driving, at least directing, and if maybe not necessarily directing, financing the development of new ideas. Elon Musk, we have SpaceX, we've got Tesla. There's new things that are being made, at least under his direction / financing. And by him doing that, we get these major leaps in technology. And as we get these leaps in technology, and we really begin to understand the power of these new ideas and inventions, maybe that can help us understand why and how some countries grow faster than others and why some are already more developed than others. Now, if we have all, or really mostly all, countries growing, the idea should be that you'd see per capita income increasing with it. And here, we really tend to think of growth as an increase in per capita income. So if everybody's growing, if every country is growing, then everybody should be getting richer. If everybody's getting richer, you'd think maybe the differences between the rich and the poor should be getting smaller. So, like the income distributions should be shrinking a little bit. You'd like to think so. So, are these differences getting smaller? Namely, are we seeing any convergence in the growth in income? Well, if we look at this data using real GDP for the world over time, source being the World Bank, it's probably a really good idea to especially cite your sources, because if the president of Harvard can get shit canned for plagiarizing, then anybody can. So let's look at the mean per capita income. So that YPC, that's income per capita. Well, in real terms, it's almost quadrupled in 45 years. But the spread, right, the width of that distribution has also been increasing. So there's no real like convergence going on. We can see that over time, that distribution in the income is also changing. So I don't know, maybe there's like some convergence to like different peaks. But for GDP between 1960 and 2010, there were a lot of countries that grew way faster than average, the Asian tigers being a few of them. And then you also had some countries that grew way below average, namely sub-Saharan African countries. So you had some countries that grew a lot faster, some countries that grew a lot slower. So maybe that is kind of describing some of this variation and this lack of convergence that we're seeing in the data. So if we want to learn more about that, probably a good idea to start learning about the actual model. So first, when we're going to learn about this model, we really need to find a way to describe the whole economy. And maybe that sounds like a lot at first, but it's actually pretty simple. Maybe you're thinking like, well, we need all this, like, we need to look at all the different types of consumer goods. And then with the different types of consumer goods, like, these different industries, there's like these little sub-industries underneath. And we got to look at every company and how much each company's making. Scratch that. You don't need to do any of that. Because all you need to do is just look at the sum of all finished goods and services produced in the U.S., which is GDP, gross domestic product. GDP is given by Y equals C plus I plus G. And this is like an equilibrium condition where you can think of output Y having to be split between consumption, investment, and government spending. So the left-hand side is like the availability of resources. The right-hand side is the use of resources. The use of resources, that right-hand side, can't exceed the left-hand side. So you have to have equality there. Now, that's pretty easy in and of itself. But I'll make it even easier for you by saying there's no government in this model. So if there's no government, well, now GDP is just Y equals C plus I, meaning everything that gets produced in the economy is either spent on consumer goods or it gets invested. And I'm not going to get into the nitty gritty of like what these consumer and investment goods are, what output is. Just think of output as Y. It's just a finished product, it's just a finished good. And that finished product is split between what gets consumed and what gets invested. Now, if you're investing here, what you're really doing is you're saving. So in this model, savings is equal to investment. If you're ever dealing with a closed model, meaning there's no trade, there's no like international finance stuff, savings will be equal to investment. Okay, so with all that out of the way, let's go on to describe the rest of the economy. We're going to have households, kind of, and we're also going to have firms, definitely. So we'll start with households. In this model, there are no explicitly modeled households. Now, the households, can also be called like agents or individuals, but they're not included in this model. And as we're dealing like with this aggregate economy, Solow kind of argued like, okay, well, there's just this aggregate economy, so there's no point in having like individual households. Now that changed when we got to the neoclassical growth model, which really takes Solow and adds individual optimization. And the idea of this like individual optimization, incorporating it into a macro model, we can then see how like a representative individual or a representative household could respond to changes in the dynamic equilibria that we're looking at. But maybe I'm getting a little ahead of myself. I don't know. Right now, we know very little about households. All we know is that they exist and they devote an exogenous fraction of their income, S, which is between 0 and 1, to their savings, regardless of what else might be going on in the economy. So that's really all we can say for households for now. We'll get back to them in a little bit. Now, the other side of the economy we're going to be looking at is the firm. all the firms are the same, and they all have access to the same production function, or as we like to say, production technology, because economists like to use big fancy words to hopefully try to convince our employers to give us more money. Now, this gives way to the idea of a representative firm, or like a representative agent. So you get like a firm that's like a good representative of the rest of the firms. Now, all the firms in this economy produce the same good, and they've got the same production technology, which is just Y equals F of K, L, and A. K is capital, L is labor, and then A is something else. I don't really want to ruin the surprise of what A is just yet. Maybe in the next slide or two. Hey, what do you know? I'm going to ruin it here. So, we're going to use a specific production function here, which is a Cobb-Douglas specification. If you've taken intermediate micro, then you have seen a Cobb-Douglas function before. We have Y equals A times K to the alpha times L to the 1 minus alpha. So K, or K sub T, is the amount of capital at time T, and L sub T is the amount of labor in the economy at time T. Finally, A is technology. Now, A is a unitless measure, so it's not like I have, A 0.5 units or what. No. It's a unitless measure. It's really just like a shifter. If A is larger than 1, what it's doing is it's shifting the production function upwards, mathematically speaking. Economically speaking, what's happening is it's making production more efficient. It means that you can produce more with the same amount of inputs as what you had before. Now, that exponent, alpha, is capital's share of income, and it's between 0 and 1. So if alpha is between 0 and 1, what this is telling us is that, looking at equation 4, it's homogeneous of degree 1, meaning if you were to add those exponents, alpha plus 1 minus alpha, you get 1. And that gives us what's known as constant returns to scale, which we'll be learning about in a little bit. So what's this shifter A thing going to look like? Well, if you were to graph out that production function just in terms of, say, capital here, you'll see it begins at 0. This production function always begins at the origin, and you're going to get something that looks kind of like this. Looks almost like a square root function, right? Now, when you get an increase in A, what's happening is it's shifting this production function upwards. It still starts at 0. It still starts at the origin, right? But it just pivots it upward a little bit. It lets you make more with the same amount of capital inputs as what you had before. So you can use 5 capital inputs and get, 2 units of output. Or you can, with this increase in A, you can have 5 capital inputs and get, say, 3.5 units of output instead. So you're using the same amount of capital, it's just you're getting more out of it. It's like more bang for your buck. Now, A is called total factor productivity, and it increases the productivity of both capital and labor equally. An example of this could be like the cotton gin, which made it easier to separate the seeds from the cotton after it got picked. So you could produce more cotton, but in less time with less damage to your fingers and your hands. It was an incredibly awesome piece of equipment. Now, a lot of you would be like, okay, there have been so many different inventions. Why are you doing the cotton gin? Well, the thing is, the cotton gin made really, capital and labor more productive. Maybe equally, we'd see. So I kind of use it for that example. So don't read too much into it beyond that. But another example of a technology increase of some sort would be the electronic head massager. Now, my fiance, soon-to-be wife, is very pregnant. She is about 5 months pregnant now. We have a beautiful baby girl that we've already named Bella, who's due in the middle of May. Hopefully, she shows up in the middle of May, so this course is already completed by then. But if not, I have already made arrangements such that the course can still carry on as planned. So she is pregnant. And when she goes to sleep every night, she gets really tired and she's not really feeling very good because pregnancy, I can tell it does a number on your body. And I myself have never been pregnant, but I tend to think of myself as a fairly empathetic individual, and I can see that it's, really doing a number on my fiance. So I try to do nice things for her. I try to keep her comfortable throughout the day, and I definitely try to keep her comfortable at night. And I, rub her head, kind of like massage her scalp a little bit before she goes to sleep. But when I do that, my hands get tired, and I don't complain. I'm like, oh my god, babe, my hands are so tired. Meanwhile, she's like cooking up this other human being inside of her. I'm not about to be that much of an ass. But like my hands do get tired. I have to stop for a minute to let the muscles rest, and especially my right hand for some reason. I don't know. It's maybe because I'm getting old. It kind of almost always sore these days. Maybe it's a carpal tunnel. Who knows? So I got to stop for a minute, let my muscles rest. And, when I do that, she kind of rolls over and asks, if I'm okay, what's going on. And, I got to tell her, no, I'm fine. Just, my hand's tired. But then for Christmas, one of her brothers gave her this handheld massager. And this thing is like awesome. It's, like this like little circular thing with like a handle on it. And it's got these four little like feet on it that like kind of move around, and I don't know how to describe what they look like, except if you've seen the first Matrix, those squid things that like latch onto the ship towards the end of the movie, and they start like zapping their laser through the hull, and they're trying to get inside, and you see like their little legs like on their body kind of moving really fast. It looks kind of like that. It's really strange. But it's super awesome because it can massage her scalp, and all I need to do is just hold it right over her head. And, then I kind of move it around her head, and it massages different parts of her scalp. And now I don't need to do as much because this is doing all that work for me. So I can produce more happy fiance for less effort. That would be like an example of total factor productivity, maybe at the more microeconomic level. But I can produce more for less. The marginal cost of production for me is now way less than what it was before, but there's more output that I get. So chalk one up to technology and her little brother for finding that. That was really cool. I think that thing was really more present for me than it was for my fiance, and I am eternally grateful to her brother. So anyways, technology itself isn't directly observed. Now you're probably going like, what the hell? You were just talking about all these cool examples of how technology gets observed. Yes, but the way it's observed in the model, the way we put things together in the model, not quite the same, because it ends up being measured as the difference between these measurable inputs, like the amount of capital and labor that we have, and output. So we have values for output that get observed, GDP. We've got measurable inputs for capital and labor. We fit that to that Cobb-Douglas production function. We know K, we know L, we know Y. We estimate the relationship between the two, and the difference between what gets estimated and what gets observed is treated as technology here. So because we're not directly observing it, really what we have to do is we have to like infer what it is after the fact. For those of you that have had statistics or maybe econometrics, I don't know if econometrics is a requirement, but if you've taken either, think about that residual. So you got like y equals x times beta plus epsilon. That epsilon is actually here. That is technology. It's the total factor productivity. And it can show up in one of three ways, according to this model. There's Hicks neutral technology, which is what we're looking at, total factor productivity, where it increases the productivity of capital and labor equally. There's Harrod neutral technology, which is capital augmenting technology. It's like a technology increase that makes capital more efficient, but it doesn't affect labor. And there's labor augmenting or Solow neutral technology, which is making labor more efficient than capital is. Now, in reality, probably more you're probably looking at more like a labor augmenting technology rather than like a total factor productivity or capital augmenting technology. But for the interest of simplicity, at least a little bit with this model, so I've already made things kind of advanced by teaching you a lot of this math. I don't need to make things worse on you. We're sticking with total factor productivity, but Harrod or Solow neutral technology is probably a little bit more realistic. Now it's going to be shifting that output curve up by less because it's affecting just the like capital term or just the labor term. Because really, if you think about it, like is there any real technology that's equally increased both factors of production? The answer would be probably not. Okay, and well, I took a minute and a half break. I'm sure you probably noticed something looks very different here. I actually caught a mistake, and I really didn't feel like going back and fixing it and starting this lecture all over again. So it has to do with this part and this part of the Cobb-Douglas specification, because originally, well, it wasn't really working out the way you'd think it would need to. So here we have like A times L to the power of 1 minus alpha in equation 3 there for the Solow neutral technology. This is where it's actually making labor more efficient or more productive than capital is. So it's just a minor mathematical error on my part. And yeah, I really didn't feel like going back and starting this whole lecture over again because, well, to be honest with you, I don't know how to fix things in post. I should probably learn, but, well, that's for future Jeremy. Screw that guy. So anyways, here's a couple of conditions we want to put on the production function. First, the production function is homogeneous of degree 1. That means we have constant returns to scale. If you double the inputs, you're going to get double the outputs. Second, the production function is increasing in capital and labor. So the more capital or the more labor you put in, the more output you'll get out. Now, this always holds for this production function. Next, the production function exhibits diminishing marginal returns. So the more capital you put in or the more labor you put in, the smaller the increase in output you're going to get. So output's increasing everywhere, but it's increasing at a decreasing rate. So this tells me that capital, or that this production function, will have a positive first derivative and a negative second derivative. So if you were to look at the production function in terms of capital and labor, this is what you see. It's increasing everywhere, but at every point moving, starting from 0, moving outward, you'll see that the slope is decreasing. So it's becoming each individual or each additional unit of capital or labor is adding to production, but it's adding less to production. Now, the first derivative, right, F sub K and F sub L, or the marginal product of capital and the marginal product of labor, it's going to be positive everywhere, which means if you increase your inputs anywhere in positive K or L space, you're going to get an increase in output. So the first derivative for both capital and labor is going to be positive. So if you plot out that first derivative and it's ever above 0, well, it's a positive first derivative. Now, as soon as it goes negative, well, it's negative first derivative. That is telling us that it's now decreasing. So you'd get if you were to add more capital, you'd get less output or something. But that's never the case with this particular production function because, well, it's increasing everywhere. So it's one of the nice mathematical properties of the Cobb-Douglas production function. So no matter how much capital or labor you get, you're always, always, always going to get more output. But the amount that output increases is by less and less each time. So what is this? Well, our second derivative will be negative. So if you were to plug in any K or L for the second derivative of this function with respect to capital or labor, you'll see you get a negative value. So because the first derivatives are positive, the second derivatives are negative, this production function is what's known as concave. So this is what the second derivative plotted out looks like. You can see it's below 0. So if that function's below 0, then, well, negative second derivative. Okay, there's a couple other conditions. I'm really not going to get too far into these because they're not necessary. You don't have to prove any of this. You don't even have to prove any of this stuff. This is just something that I need you to remember throughout the course. We have these Inada conditions. Basically, it says if you have almost close to 0 inputs, the marginal product of capital or labor is going to be really, really high. And as you add almost infinitely many inputs, the marginal product of capital is going to be really, really low. So really, it's just kind of describing the shape of the first and second derivatives of the production function. Now, this holds for all Cobb-Douglas production functions. One of the really nice things about it. And it's actually why we're going to be using a Cobb-Douglas production function throughout the course. It's got some very nice intuitive mathematical properties, and yeah, it's nice to use. So something I want to note really quickly, this production function always starts at the origin. So if k equals 0 or L equals 0, then y is equal to 0. I actually encourage you plug in a positive value for one of the inputs and 0 for the other and see for yourself, see what you get. Now, if there's a shift in A and you have to draw that shift, which you will at some point in the class, that production function is going to pivot around 0. So regardless of what A is, the function will always begin at the origin. So make a note of that, highlight it, underline it, maybe make another note that's like italicized, make another one that's bold. Just don't ever forget that this thing begins at 0. I've, in the past, graded exams and homeworks and stuff like that where it begins, like somebody drew it where it begins like higher up the y-axis or something. I'm like, no, it doesn't do that. It always pivots because, well, mathematically, if you try to say there's a y-intercept other than 0, well, it would be wrong. And if it's wrong, it's not right. Okay, so more assumptions about the firm. It's enough math, at least for right now. All of the goods and factor markets in the model are competitive. So households and firms are price takers. They're not setting prices at all. They all pursue their own objectives, and prices clear all the markets. Labor gets supplied inelastically, which means that for some non-negative price W or wage rate, all the available labor gets supplied. Households own the capital and they rent it out to firms. They do so at a price of R, which is the real interest rate. And while these prices do exist, they're not explicitly modeled here. So you're not going to be seeing wages or interest rates in this model. We could include them. We will in future models, but we don't really need to use them here. And we'll kind of get into why a little bit later. So we got a lot of the firm stuff down. A little bit more on them later. We've covered a lot of the supply side. Let's go back to that demand side. So we know the household is going to be faced with a choice between consuming C or investing, which is I, saving. And they save a constant fraction of their income, and they consume the rest, which is 1 minus S. So why would you want to save? Well, if you save today, you consume less today, which really sucks for you, right? So you need to have some incentive to want to save, namely like some kind of positive return on your investment. If you let somebody borrow your money today, they pay it back tomorrow plus interest. So the interest you get back allows you to be able to consume more tomorrow than you'd be willing to, spend today. So you save today, consume more tomorrow. You're happy. The other person you lent the money to is happy, except for, when they have to repay it because that sucks. But hey, that's life. Everybody's happy-ish. So you consume, that's C. You invest, that's I. What are you getting when you invest? Like what's actually happening? Well, you're getting capital. So investment here is a function of capital, where KT plus 1 is tomorrow's capital, which is chosen today, and KT, which is today's capital, was chosen yesterday. So capital is what's known as a state variable. We can't affect current output by changing current capital because it was chosen yesterday. And we have delta, which is between 0 and 1. It's the rate of depreciation of existing physical capital. It's the percentage of capital that needs to get replaced each period. So this investment is a flow of capital over time. It's new capital minus old capital, but that old capital is falling apart at some rate delta. So new capital minus old capital. I guess I should really say old capital, but not 100% of the old capital moves into the next period because this delta, this amount delta, this rate of depreciation, cuts, say, 2%, 5%, 10% of the existing capital stock that then needs to be replaced. So if you have, say, delta is equal to 0.05, 1 minus 0.05 is 0.95, 95% of existing physical capital carries over into the next period. So let's do an example, right? Investment's a flow equation, implying it's the flow of capital over time, or the change in capital over time. So let's just say KT plus 1 is 110, KT is 100, delta is 0.05. Well, with these, we just plug them in for that law of motion of capital. This right here, this investment equation is called the law of motion of capital. You plug that in, plug them in for each variable in equation 9. You get 110 minus 1 minus 0.05 times 100. Simplify that out a little bit. 110 minus 0.95 times 100. 110 minus 95, that gives you 15. So investment is 15 units of capital. So 15 units of capital have been added to the capital stock. Now, what happens if the depreciation rate increases? Well, let's do another example. Delta is now 0.1 or 10%. So everything else is the same. You still get 110 for KT plus 1. You have 100 for KT. It's just now instead of 0.95 times 100, you get 0.9 times 100, which is 90. So you get 110 minus 90. Investment is 20. So you can see investment increased from 15 to 20 units of capital. So if delta goes up, if the rate of depreciation goes up, right, delta, then investment goes up, which you'd think could be a good thing, right? But maybe not. Let's look into it. Because if you invest more, you're consuming less. Because remember, you can consume, you can save. If you save, you invest. If you have $100, you can consume 50 of it, you save 50 of it. You need that incentive to do so. That incentive is generally more output tomorrow, which, so the idea is we choose KT plus 1 for tomorrow. If capital goes up, output goes up because, well, that production function that we looked at. So if investment goes up, doesn't output go up? Well, sometimes, but not always, because, see, investment's got a couple of moving parts here. If investment increases, it can be because of two things. One, KT plus 1 increased, which is good, right? You're increasing the capital stock. But if depreciation increases, that's not good. An increase in KT plus 1 means an increase in future output. There's more existing capital stock that can be used to produce. The more capital you have to produce, the more stuff you can have tomorrow. But an increase in delta doesn't mean an increase in future output because now we're consuming less just to be able to replace the existing capital. So it's not like you're consuming less to get more tomorrow. You're actually consuming less to get the same amount you would have had tomorrow. Output isn't increasing if delta increases, thus increasing investment. We just consume less to have the same amount of stuff as before. So that sucks. So an increase in investment is not always a good thing. It depends on what's driving that increase in investment. If you're saving more and, capital's not falling apart at a faster rate or anything like that, an increase in investment means more production tomorrow. That's good. Depreciation increases though. Well, you got to save more, you're consuming less, but that's just to keep output where it was before, which sucks. That's not good. So let's put some of this stuff together because we learned about GDP, we learned about the production function, and we learned about the law of motion of capital. And we can put these three guys together. Now, GDP, equation 11, is what's known as a resource constraint because it's a constraint on how our resources can be used. So think of Y as like available resources today, and it can be consumed or it can be invested. You can't, C plus I can't be greater than Y because, well, there's no more stuff than the stuff that got made, right? If you produce 100 units of output, you can't spend 105 units because you made 100 units. And so equation 11 is a constraint on how our resources get used. Equation 12 is the production function. So this is A times K to the alpha times L to the 1 minus alpha. And then we have our law of motion of capital. So we got three equations. And having three equations is cool, but what's even cooler is having just one equation. So we can actually combine these guys and just substitute some variables out and have everything in terms of, say, C, K, KT plus 1, and right now L, but that won't be for long. So if I can just take these three equations, reduce them down to 1, I'll be a lot happier. So the first thing I'm going to do is I'm going to look at that resource constraint. I got a Y in there, right? Now, if you look at equation 11 and equation 12, Y is like that nice magenta, pinkish color, whatever it is. It's really pretty. But if Y is equal to A times K to the alpha times L to the 1 minus alpha in equation 12, and you have Y in equation 11, well, that means you can substitute Y out for A times K to the alpha times L to the 1 minus alpha in equation 11, and that gives us equation 14. So I currently have a times k to the alpha times L to the 1 minus alpha equals C plus I. And now I want to get rid of I. I want to get rid of investment. So I'm going to take equation 13 over here. And because, well, I've got I here in the resource constraint, and then, oh God, what the hell happened there? I've got I here in equation 13, and I is equal to all this junk. Then I can just take all this junk here, plug it in for I here. It's exactly what I do to get equation 15. So now I've reduced those three equations down to one, which is a lot easier to play with. Now, I don't know why I put this in here. I guess I just thought it was cool or something. I don't know. NyQuil on the rocks is fantastic, by the way. So if you're ever having a really tough time, with your cough, you're sniffling, you're sneezing, you want to hang out with your cat, think your cat's Elvis, you want to hang out in the clothes dryer and act like you're in a little rocket ship or something, NyQuil on the rocks is great. NyQuil Old Fashioned is also really, really good. The magic of NyQuil. Okay, so enough about that. We learned about the motivation for the Solow model. We learned about who the players were in the economy. And we learned about breaking that aggregate resource constraint down and expressing it in terms of capital, labor, and consumption, or all of the endogenous variables. Now, the next time, what we're going to be doing is expressing it in terms of effective labor units, meaning everything is like a per unit of labor. And this is actually allowable because the production function is homogeneous of degree 1. There's no proof necessary, just take my word for it. But then what we're going to do is we're going to solve the model out, get the steady states for capital, investment, consumption, and output. And, well, until then, thank you for watching. The next video will be available in a couple of days. So make sure you take really good notes on this video. And, well, I'll see you next time. Thanks for watching. Bye.